Today we're going to be talking about exponential equations. Our objective is that we will be able to write an exponential equation and we will be able to use an exponential equation to predict a future value. So exponential functions have the form y equals a times b to the x exponent, x power. So a is our initial value. And b is our growth or decay factor. So, if you assume that inflation increases somewhat and remains 3% per year for the next decade, what is the growth factor for a 3% increase? We would add that 3% to 100%, which would give us 103%, which is 1.03 as a decimal, so that would be our growth factor. If a pizza is $8 currently, write the model for the cost of the pizza, where y represents the cost and x represents the number of years from now. So we'd have y equals, our initial value is $8 times our growth factor of 1.03 to the x power for the number of years that go by. So if the annual inflation rate stays the same at 3%, how much will a pizza cost in 20 years? Everything would stay the same. We would just plug in 20 where the x was, since that was representing the number of years. And when we type that in a calculator, it comes out to be 14.45 when we round to the nearest cent. Use Desmos to determine when the price of the pizza will double. So the price, that's our y value. If the pizza is going to double, that would mean it's no longer $8. We want it to be $16. So we would graph y equals 16 and y equals 8 times 1.03 to the x power. Now this can also be solved using logarithms, but that's not something we learn in this class, so we're going to solve it by graphing. So in Desmos, I'm going to put in y equals 16, and then I'm also going to put in y equals 8 times 1.03 to the x power. Now you can kind of see the graph up here a little bit. I'm going to zoom out till I see both of my graphs. I know I'm looking for red and blue because those are the colors on the side, and I'm looking for where they intersect. So they both equal 16 when x is 23.45. So I would know x equals 23.45. So in 23.45 years is when the price of the pizza would double. All right, Archibald purchases a new car for $16,000. Archibald soon finds out that his new car will depreciate by 15% a year, according to Edmunds.com. What is the decay factor for the yearly depreciation rate of 15%? Remember, we subtract that 15 from 100%, which would give us 85%. So our decay factor is 0.85. Write the model for the value of the car, where x represents the number of years of ownership and y represents the car's value. So y would equal our initial value of the car, 16,000, times our depreciation rate to the x power. So determine the value of the car in 8 years. That's an x value. So 16,000 times 0.85 to the 8th power. Type that in a calculator. And it would come out to be $4,359.85. Determine how long it will take for a car to decrease to half of its original value. So it was originally worth $16,000. We want to find out when it's worth $8,000. So we'll put that in Desmos as well as our original equation. And again, we're going to see where they intersect. Now, we're dealing with values like 8,000 and 16,000. So that's going to be like way off this graph patch. So I'm going to click the gear and my y-axis. I'm going to jump that up to, let's do 6,000 and then the max. I'm going to bump up to 10,000. I just picked two numbers that are a little bit lower than the y value that I was given that I know is going to be my horizontal line. So they intersect at 8,000 at 4.265. So it would happen in 4.265 years. That's when it will decrease to half its value. All right, now what if we're just given data, we're not given the percent increase or percent decrease? So the following table shows the rapid increase in cell phone users in the late 1990s. So we've got the years and how many cell phone users there are. First, it asks us, is the data linear? So from 96 to 97, it went up by about 11 million. Then it was 14 million. Then like 17 million. Then like 22 million. So it's not linear. It's not consistently increasing. We're not adding the same thing each time. If it had gone up, like the first year, it went up by 11 million. If it had gone up by 11 million every time, then it would have been linear. So let's compare the ratios of what we had in 97 to what we had in 96. And what we had in 98. To what we had in 97. 99 to 98. And then finally 2000 to 99. So if we divide all these, let's see if they give us. First one gives us 1.25. Second one gives us 1.25. Third one gives us 1.25. And the last one would round to 1.25. So, does the relationship in the preceding problem represent an exponential function? Yes. All the ratios were the same. And what's the growth factor? Well, the growth factor is that ratio of 1.25. So now we can write the equation. Our initial amount of cell phone users was 44.248. So y equals 44.248 times our growth factor of 1.25. And it's telling us this time to use t as the number of years. So to the t power. All right, so now we're going to use our equation to estimate the number of cell phones in the year 2005. Now, important thing to remember is this. It told us that t started in 1996. So, 2005 minus, oh, I'm still on highlighter, minus 1996 means 9 years have gone by. So that is what we're going to put in for t. So y equals 44.248 times 1.25 to the 9th power. Which gives us 329.673. Now let's look at our units, because there's no way there was only 329 cell phones in 2005. So it told us it's the number of cell phones in millions. So there's 329.673 million cell phones. Then, using your graphing calculator, determine the number of cell phones, when the number of cell phones will be 150 million. So it's giving us that a y value again. We know it's 150. We just talked about how our units were in millions, so we just need the 150 part of it. And then we'll put our original equation. Desmos won't recognize the t on the graph, so we need to put an x. So this would be 150, 44.248, growth factor of 1.25. So remember, we're up in the thousands. I did give you a hint to make your lowest y 100 and your higher y 200, because we want 150 to be in the middle. Well, and now we're able to see our graphs, and they intersect at 5.471. All right, so this asks us when, and let's think back to how everything was written. We were given years, not like number of years. So since we started in 1996, and this is approximately 5 years later, we would say in 2001. If you wanted to round up and say 2002, just because it's almost like halfway through the year, you could do that. So basically we're adding 1996, and because it's a year, we're not going to leave it as 2001.471. That's just not how we write years. That's all for today. I'll see you in class.